Hi everyone, my name is Yingtong. I'm going to present our work on Mousse. This is a joint work with my collaborator Hsin-Wei and my advisor Ardalan and Sani. Before I introduce Mousse, I'd like to talk about the background of the problem Mousse is trying to solve. It is a system for selective symbolic execution of programs with untamed environments. So what are programs with untamed environments? To answer this, let's first define a program environment. A program may interact with other components in the system during its execution. We define those components as a program environment. When doing analysis like symbolic execution, people can either model or virtualize the environment if it is simple. For example, file systems and networks. However, when the environment is complex, like device drivers and customized hardware, it cannot be modeled nor virtualized. We refer to such an environment as untamed environment. Programs with untamed environments are quite common in the real world. OS services is one example. More and more smartphones incorporate a large number of OS services with their unique hardware, like novel camera modules. The other example is software frameworks for accelerators. Those accelerators can be powerful GPUs in VR headsets. There are also lots of customized applications on stock Android devices. Moreover, a study conducted by OpenSignal shows the trend of customized device fragmentation is constantly growing, which means programs with untamed environments are also growing. As you can see, analyzing them is becoming really important. In our work, we focus on SSE to do this. SSE is short for Selective Symbolic Execution. It is a way to specify which parts of a big program should run concretely and which ones should run symbolically. It makes symbolic execution practical for large real-world softwares by reducing path explosion problem. There are two existing approaches for analyzing programs with untamed environments using SSE. The first one is symbolic environment. In this approach, it replaces the real environment with a symbolic environment. The symbolic environment simply drops any write operations from the program and returns a symbolic variable to a read operation. But it has three problems. Since it is using a symbolic environment, it has no knowledge of how the environment should interact with the program correctly. So it is inevitable, it causes false positives and has path explosion problem. In our experiment to analyze an Android OS service, it couldn't lead us to fully initialize the service. The other approach is decoupled execution. It has a concrete execution engine on the device with the environment and a symbolic execution engine on an external machine to do analysis. To use it, the concrete execution engine runs the program until a predefined event occurs. At this point, to do analysis, the symbolic execution engine synchronizes the memory from the device and continues its execution. Later, when the analysis is finished, the execution of the program can be transferred back to the device. One apparent drawback of this approach is it causes significant overhead because of memory synchronization. We tried both approaches to analyze an Android OS service, but failed. So we introduced Mousse. It is tailored for programs with untamed environments, achieving three important goals. It needs to use real environments correctly without modeling or virtualizing. We hope it can give us high performance. Last but not least, we hope it can be easy to use in terms of its deployment and no additional engineering efforts required. Now let's dive into Mousse's three solutions and see how it achieves its goals. The first one is process level SSE. To explain how it works, let's first look at VM level SSE, which is pioneered by S2E. It has the program in the virtual machine and the SSE engine in the hypervisor. To use it, the analyst starts the program in the virtual machine and the SSE engine analyzes the whole virtual machine selectively. But it does not work for programs with untamed environments because it requires virtualization. Some hardware components in untamed environments do not support such technique. To eliminate the requirement of virtualization, Mousse proposes the solution of process level SSE, which means it simply launches an OS process on the device with the environment. To do this, it takes the program and the SSE engine from VM level SSE, and then composes those two components into one OS process to do analysis. This solution makes Mousse easy to use. To use it is like simply launching an OS process. It also uses real environments. However, this solution alone cannot fully satisfy this goal. That's why we need our second solution, which is environment-aware concurrency. Here is one example to illustrate how it works. Assuming the left side is a program's execution tree, at first only path 1 is executing. Then the program sees a predicate on a symbolic variable. The SSE engine forks another process to execute path 2. As both of them are executing, they want to issue an environment called A, in other words, equal A to the environment. However, without expecting multiple concurrent equal A from user space, the environment may see conflicts and returns an error. This is because both of the processes are using the same real environment, so blind concurrency does not work. To solve the problem, we added a component called environment-aware concurrency. It simply answers a question, is this equal allowed in the process? In this case, the answer for path 1 is this equal is a state mutating equal and is allowed. Here we define a state mutating equal as when executed, mutating the state of the environment in a way that could affect the execution of another path. But for path 2, the answer is this equal is rejected to keep the environment consistent with path 1. By using this solution, path 1 and its children are able to finish their executions. This solution and process level SSE together make using real environments realistic. It also improves performance by allowing some concurrent path to finish correctly. However, to execute more paths, we need another solution, which is distributed execution. Here we use the same example we had before to see how it works. We start the program on device 1. When path 2 is rejected because of state mutating equal A, device 1 offloads path 2 to the server. Then a standby device, device 2, can download the path from server to finish its execution. Distributed execution and environment-aware concurrency together help improve Mousse performance greatly, as I will show you later in our evaluation. By using 3 novel solutions, Mousse is able to achieve all its goals. Now let's talk about evaluation. We conducted experiments on 5 Android OS services in 3 smartphones to evaluate Mousse performance, code coverage, and analysis results. Our evaluation shows environment-aware concurrency improves execution time. In this experiment, we tested 2 APIs of the audio provider service in Pixel 3. In this figure, the x-axis is the maximum number of concurrent paths allowed on each device, and the y-axis is the execution time of finishing one API. The first API has no state mutating equals, resulting 59% improvement. The second API issues state mutating equals, which limits concurrency. However, even in this case, the improvement is 24%. We also evaluated distributed execution by using the same 2 APIs. In this figure, the x-axis is the number of smartphones being used, and the y-axis is the execution time of finishing one API. Besides, we fixed the number of maximum concurrent paths on each device to be 9. For the first API, the improvement is 63%. and for the second one is 64%. By using environment-aware concurrency and distributed execution together, for the first API, the improvement on execution time is 84%, and for the second one is 73%, which both show great improvement. We did more experiments to evaluate Mousse. We compared Mousse with a symbolic environment and a simple fuzzer in terms of code coverage. We did bug findings, tint analysis, and performance profiling. More importantly, we conducted large-scale experiments to measure the execution time of more APIs in different services. Please refer to the paper for more details. To conclude, we introduced the Mousse, a system for analyzing programs with untamed environments using SSE. It outperforms alternative solutions in terms of performance and code coverage. It also opens the opportunity to perform various analyses on programs with untamed environments. Mousse is open source in the hope of benefiting the community. Thanks for listening.